Hello students, welcome to the second lecture on the course Mathematical Modeling and Simulation. So in this lecture we will see some methods of mathematical modeling. This mathematical technique will help us to see that or check whether our mathematical models are correct or not. So the first method is checking the dimensional homogeneity and consistency, then abstraction and scaling, conservation and balance principle, and then constructing the linear model. So these all steps will help you to build up the mathematical modeling. Now I will discuss the outline of this lecture 2 and 3 because 2 and 3 are mainly concentrated on this first point, that is the dimensional homogeneity and consistency, and these two are related, but I'll discuss all these things in the other lectures. But the main aim of the second and the third lecture is to discuss this part, is to check dimensional homogeneity and consistency. So I'll tell you what do you mean by dimension, unit and dimensional homogeneity of the equations. We will understand the various benefits of dimensional analysis, and then we will see how to use the basic method and Buckingham pi theorem to identify non-dimensional parameters. So let's start. What are dimensions and units? So dimension is, as you might have already known, that dimension is a measure of a physical quantity which does not have any numerical values. For example, we may say length, time, mass, or the combination of these are the dimensions. So if a dimensions to a physical quantity is given, then it will not change, like it will be same every time. Now there are 7 primary dimensions. These are also called as fundamental or basic dimensions. So if I list, this is mass, length, time, temperature, electric current, amount of light and amount of matter. So these 7 are called as the primary dimensions or fundamental dimensions. So these are the 7 primary dimensions, as I have told: mass, length, time, temperature, electric current, amount of light, amount of matter. So now we will write down the symbols what I will be using in this course. For M, for mass, I will use M, capital M in a big bracket to denote the dimension of the mass, length with capital L, capital T for time, theta for temperature, electric current with I, amount of light with C, capital C, and amount of matter with capital N. So these all are the representing or symbols of the dimensions of these 7 primary dimension, and every other physical quantity will be the combination of these, right? So the dimension of a physical quantity can be expressed as in the terms of fundamental dimensions. What I have already told you, that if you have any physical quantity, then its dimension can be expressed in terms of these fundamental dimensions. So let's see the dimensions of force. Now you know that force is what? Force is mass into acceleration. Now I will write down force is equal to mass into acceleration. Now if you talk about the mass, the dimension of mass is given as this, and what is acceleration? The dimension of acceleration, I will represent the dimensions in this big bracket, right? And the dimensions of acceleration is what? This is Lt minus 2. So what will be if I talk about dimensions of f? So the dimensions of f will be equal to m L T minus 2. So this is the dimension of force. So with the help of all these 7 primary dimensions, you can find out the dimension of any physical quantity. So here you have find out the dimension of force, which depends upon what? Mass, length and time. Now we will see what is unit. So a unit is a way to assign the number to the dimension. So for example, length is a dimension, right? If we say length, then it is a dimension, but units are what? We have units such as feet, centimeters, meters, kilometers, and many more. So you can see that the dimension is unique, but units may change. So when we work with the physical quantities, we need units, and as we know, there are huge amount of units. When the unit change, the numerical value of the quantity also changes. You know, as you can see, if I draw a scale, okay, so this is a 3 centimeter scale. So what is this 3 centimeter? This is a unit. I'm saying 3 centimeter scale, this is a unit, but what will be its dimension? Its dimension will be length. That is, I can write it as this represents the dimension. However, you know that 1 inch is equal to 2.54 centimeter. So I can call either this as 2.54, this much as 2.54 centimeter, or I can call this much length as inch. So now you can understand that we have huge numbers of units, but the dimensions is fixed, that this is a dimension L, that this is measured in length. So I hope the difference between the dimensions and unit are clear. Now we will see what are the advantages of dimensional analysis, why we need to know the dimension. So with the help of the dimensional analysis, we can check the correctness of the given relation. We can determine the dimensions of unknown quantities, like which we have some unknown quantities, we can determine the dimensions also. Then defining the dimensionless constants or unit. For example, you may take that Prandtl number or Reynolds number. Reducing the number of experiments to be conducted. Obviously, if we create some dimensionless constant, this is related to third point, that if we create some dimensionless constant, obviously our numbers of parameter will reduce, and this will reduce the number of experiments to be conducted. Then we can also derive the relationship between various physical quantities, and obviously conversion of one system of unit into other system of unit. Like if we know, if we want to go from one system of unit, like from centimeter to meter or from meters to kilometers, so we can convert easily if we know the dimensions of the equation. Now, how to check the correctness of a given relation, or you can say the dimensional homogeneity. You know that every additive term in the equation must have same dimensions, right? If we have one equation, then every term, if you see this as term, then every term must have same dimensions. But if you see that additive terms have different dimension, right? If you see that the two terms have different dimensions, that if you see in the figure, this is looking like different, considered it as different dimension, then you have made an error at some earlier stages of analysis. Then it would be a clear indication that if you are adding two different dimension terms, then you have made some kind of error. Now we will see that how we can derive a relationship, or we can deduce an expression for the unknown quantities. So consider the problem of the pendulum. Now you need to find out the expression for the period of oscillation of pendulum. You need to derive the expression for period of oscillations of a pendulum. Now you can see that this problem mainly consists of three possible variables, that is mass of the bob, this length, and the gravitational force. So this we have to first list the possible variables. So the possible variables are L. Now what is the dimension of this length of the bob? Obviously this will be L. What will be the dimensions of M, mass, right? The dimension will be given as this, and what will be the dimension of G? This will be equal to L T minus 2. So these are the possible parameters or possible variables that are involved in the problem. Now we know that period dimension will be what? Period dimension. I will call the period as P. Now this dimension will be clearly T. Now we need to look for such variable combination which is equal to, like, which is equivalent to T, because we need to find out what? We need to deduce the expression for the period of oscillation, right? We need to find out this P. Now the only possible combination you will see that if we divide this L and G. So if we see that if we divide this L and G and take the square root, its dimension will be equal to what? The dimension of this will be equal to, see, this is L, right? And this is, it is given over here, and if you divide you can see that its dimension will be again equal to T, which is the dimension of this period P. So from here you can find out the expression, because you don't know anything about its physics. Even then, if you know the variable involved, what you can do, you can have some idea about the formula, because we haven't talked about the physics, but still you are able to derive the expression. So this is the power of dimensional analysis. If you see here, the mass is not involved. Here you were getting this, and you can note that mass is not involved. But the actual equation is what? This is equal to, when we remove this sign of proportionality, we will get this. Now this is dimensionally homogeneous equation which is independent of the system of unit chosen or measure length and time, right? On the other hand, what you can do, if like this one is independent of system of unit chosen, but on the other hand, if we put value of G as 9.8 meter per second square, and if you know that the value of pi is approximately 3.14, now if you put this value in this equation, then this will be equal to approximately equal to 2 under root L. Now I will call it as equation number A. So can you just see that this equation number A is only valid when we measure the length of the pendulum in meters, right? Then only this equation is valid, otherwise it will give the wrong result if you take the length in some other than meters. Now this one is case 1. Now case 2, if we put G is equal to 32 feet, now what will happen? This will be equal to, P will be approximately equal to 1.1 under root N. Now you can see that this one is valid, this equation number B is valid only when we take the length in feet. This was valid, this A was valid when you take length in meters. This is valid only when you take the length in feet. So equation A and B are not dimensionally homogeneous. So you can see that these formulas may be appear appealing and elegant, but you need to remember that these have some limitations. So this was one of the advantage of the dimensional analysis. Now we will look on to the another example of the Bernoulli's equation. So as you know, the standard form of the Bernoulli's equation is what? This is P plus half rho V square plus this G Z is equal to some constant. This is an equation for an incompressible irrotational fluid flow, where this P represents the pressure exerted by the fluid, and this one is the density of the fluid. This is what? This is velocity of the fluid, and this one is the height of the container, right? And this one is the constant. Now what you need to do is that you need to verify that each additive term in this Bernoulli's equation has the same dimension. That means that you have to see that whether all the terms what we have added have the same dimension, and secondly what will be the dimensions for this constant C. So let us do this. As you know, the pressure is equal to what? Pressure is equal to force upon area, right? So what will be the dimension of the force? This we have derived already. So this will be the dimension. This will be having dimension of L square. Now you can see that the pressure will have dimension of this, right? So this is the pressure, so it has a dimension this. So this one was the first term in the Bernoulli's equation. Now what will be the dimension of the second term? This was what? This was the density and this was velocity. So density is what? Mass upon volume, and then I can write this is velocity. So velocity has a dimension of length upon time, and this is square. This half is a constant, it doesn't have any dimension. So finally what I am getting, I am again getting the dimension as this. So this term also has the dimension, same dimension as the above. Now the third term, that is rho g z. Now this one is what? This one is density, again mass upon volume, into what? This is g, that is a kind of acceleration. So the dimension will be length upon time square. And what is this? This was the height of the container, so the dimension will be equal to length. And finally you will see that you get a dimension of this. So by this you can see that all these three have the same dimensions. So this equation is dimensionally consistent. So you can say that all three additive terms have the same dimension. Now what is part B? In part B we need to tell about what are the dimension of the constant. Now from the law of dimensional homogeneity, the constant must also have the same dimension as of the additive terms, right? So thus what will be the dimension? This will be, it will have the same dimension according to the law of dimensional homogeneity. Now we will see few remarks. So you already know, according to the dimensional homogeneity, that each term, like each additive term, will have the same dimension. Now it means that if we divide each terms by some collections of variables or constant who have the same dimension, then the equations is rendered as non-dimensional. For example, if we see our Bernoulli's equations, and if we divide this Bernoulli equation with the pressure, like this one is also having the dimension of pressure. So then if we divide each term by this term, then each term will have what? The dimension as 1. So this is called as a non-dimensionalized form of Bernoulli's equation. Obviously each term in the non-dimensional equation is dimensionless. You can see that all these terms are dimensionless. Now further, if we look few more definitions. So what is a dimensional variable? A dimensional variable is defined as a dimensional quantities that change or vary in a problem, right? It has dimension and it vary in the problem. For example, if you take a simple differential equation as this, here this variable z and t is the dimensional quantity that change or vary in the problem. So as I have told that this has a dimension of L length and time has a dimension t. So what are non-dimensional variables? Non-dimensional variables are defined as a quantity that change or vary in the problem but have no dimension. So this is important, that those variables or those quantities which have no dimension but they can vary in the problem. So for example, the angle of rotation measured in degree or radians, which is measured in degree or radians, are dimensionless units. Now if you look at the gravitational constant, you can see that this is having a dimension. So but it remains constant if you choose some unit, like if you are in meter second, then its value is 9.8. So this is a constant while it is having a dimension, so it is called as dimensional constant. What is its dimension? Its dimension is L t minus 2. Now this is a kind of acceleration. Now, what are parameters? Parameters is a quantity that influences the output or the behavior of mathematical objects but viewed as being held constant. So, for example, you can take this function, right, and this function. You can see that here m and c are the parameters. With different m and c, you will observe a different line. So for every problem, this m and c can change, but for one equation, like if I write fx is equal to 2x plus 3, then it is remaining constant. So these are the parameters that influence the output, because if you change this, the function fx will change. So this is a class of parameters. Similarly, if you see a, b, c are the parameters, if you change this value of a, b, c, you will observe different kind of parabolas. So this is few definitions. Now consider a simple equation of motion which is given as this, which we have already discussed. Like in this, we have a dimensional variable z and t. The dimension of z is L and the dimension of t is time. Now if we integrate this, what we will get? We will get the solution as this, where w naught and z naught are the suitable initial conditions, and this will be the solution if you solve this differential equation integrating twice. So I'll just write. Now what are these? This half and this exponent 2 are called as pure constants, and just like pi and exponential. So these are also the pure constants. Now if you see this equation, what are the primary dimensions of all the parameters? The dimensions are as follows. Z has a dimension of L, Z naught also have a dimension of L, W naught has a dimension of LT minus 1, T has a dimension of time, and G has a dimension of LT minus 2. So these are what? These are the dimensions of all the parameters involved in this equation. Now what we will do, we will introduce two parameters. One is z star, which is equal to z by z naught, and t star, that is equal to w naught t by z naught. So if we substitute these values, right, in this differential equation, we call it as differential equation 1. If we substitute these values in differential equation 1, what we are getting? This implies that I can write this equation as z naught as this, z star by dt star square. Now if you see this quantity, I can write it as Frod's number. So I will give it a name, fr square. This is equal to this. Then this gives you a dimensionless number. This number don't have any dimension, so this is dimensionless. So we call it as Frod's number. So this implies your fr will be equal to this. So now what will happen? You can see your equation of motion will now become in a non-dimensionalized form. Earlier you were having a dimensional equation of motion. Now this is your non-dimensionalized equation of motion, and when you solve this, and how will you solve? You can integrate it easily, and you will see that this implies your z star will become equal to this. Now you will think that you have went through all these kind of algebra, a lot of algebra. Then what is the advantage of non-dimensionalizing such an equation? Like before you have a dimensional equation of motion, and now this one you have derived this, I can call it as equation number 2, which is a non-dimensionalized equation of motion, and this has the solution which is again have a non-dimensionalized result. Now if you remember, the solution of the previous one had three dimensional variables, and if you can see this, I call it as equation number 3. Just see equation number 3. It contains only one non-dimensionalized parameter. So this reduces the number of the parameters. The first benefit is that it reduces the number of parameter, and secondly we can identify the relationship between the different parameters. So what is the relationship we saw? Since our fr is equal to what? This is equal to omega naught by under root g by z naught. So with the help of dimensional analysis, what we have established? We have established the relationship between the key parameters. If we double this value of w naught, it will have the same effect if we decrease this z naught by 4 times. Like all over dynamics will remain the same. So this is the first benefit, and the second is the number of parameter in the non-dimensionalized equation is less than the number of parameter in the original equation. As you have seen that in the original equation, how many parameters? There were three parameters, that were g, w naught and z naught. Original equation, three parameters. But what happened in the non-dimensionalized one? So you have only one parameter, that is fr. So you can see that how the number is decreased from 3 to 1. So this is the another additional benefit of non-dimensionalizing. So this will also help you in reducing the number of graphs to be plotted. For example, if you consider this is for the original and this is also for the original. So here in figure number A, what we have done, we have fixed w naught as 4 meter per second, and we are seeing the effect of z naught. Now you can see that the z naught is increased and how the profile is behaving. In the next figure, in figure number B, you can see that here we have fixed z naught to 10 meter, and we are now seeing the effect of w naught. Right, so we need two different figures to see what will happen if we fix omega naught, and then what will happen if we change z naught. Here change z naught, here we are changing what? W naught. But this figure C is for the non-dimensionalized equation of motion. Here we can easily see all the changes in one figure only. Here we need only one figure. You can easily choose fr. Obviously it is what? It depends on both w naught and z naught. If you can fix this and change this, you will get different frs. Now you can plot the result in the same graph, because here the fr is only changing. So you do not have to plot so many graphs like different plot. The same thing can be done, or the same thing is conveyed from the one single graph. So it reduces a lot of effort. Also we will discuss some of the disadvantages of the dimensional analysis. Till now you have seen what are the advantages, so I will list few of the disadvantages. It is limited if we have a trigonometric or exponential solution. So this is a main disadvantage, and sometimes it is very impractical to correlate more than 3 parameters. Addition and subtraction of the parameter cannot be reflected on dimensional analysis. It cannot give a final word on the validity of relationship. And the last is the analysis cannot understand the nature of the constant in the correlation, because as you have seen that in the dimensional analysis it was only saying that p is proportional to the period is proportional to L by G, but it is not giving the nature of the constant. So finally see that p is equal to 2 pi under root L by G, but with the help of dimensional analysis, the nature of the constant was, we were not able to find out the nature of the constant. So this was all for this lecture. Now we will do the remaining part on the next lecture. Thank you.